If an object is above 0 degree K, it will radiate energy as electromagnetic waves. That means you are actually radiating as electromagnetic waves, which is in the infrared range as heat. So every object radiates. So what are black bodies? Black bodies are not black, but they will absorb all type of radiation, all type of electromagnetic waves across all wavelengths, and they will not reflect any of those, but they will be able to emit waves at all wavelengths. So that's a perfect black body. So a perfect black body is a theoretical one, but we can say sun is a black body because sun radiates waves at all different wavelengths, a wide range of wavelengths. Or an incandescent lamp radiates waves at different wavelengths. So that means black bodies absorb all wavelengths and radiate all wavelengths. If I have an object that radiates, what happens is that that object might radiate some red, some green, some blue, and some white. Depending on the temperature of the object, we might have, say for instance, this object is radiating lots of red. And we have another object that might probably radiate lots of green and some red and then some blue and white. And another object might probably be radiating lots of blue and the others. So objects with different temperatures, so this one T1, T2, T3, different temperatures radiate different wavelengths at different intensities. So in T1, we see that there's lots of red and lots of green and lots of blue. That means it's radiating all wavelengths, all frequencies, but at different intensities. So scientists initially observed that they tried to draw a graph between the wavelength and the intensity. So here wavelength and here intensity. And they found out that the black body radiation curves look quite similar for all the objects with different temperatures. So one would look like this and the other one looked something different. And then the other one this. So they all look similar in terms of the shape, but they all the blackbody radiation curves of different objects with different temperature. So this is T1, T2, T3. So this is the temperature of the objects, the black bodies, could be stars, and these curves relate to those objects. So these curves were derived through experiment, through observations. They use the spectroscope to get the spectrum and then plotted the curves. But using the classical wave theory, when the scientists tried to plot the curve, so this is lambda and this is intensity, and the curve looked like this. So that's theoretical one. That's a theoretical curve, and there's an experimental one. So using the classical theory, when scientists plotted this curve, they observed that here the intensity increases as it reaches the low or high frequency range, which is the low wavelength. But the experimentally observed waves where it reaches a peak and then they come down, and you can also see that there's not much radiation in the range like gamma or X-rays. But the classical theory says that it will keep on increasing to infinity. That means that is for all the black bodies. Any black body will radiate like that. So there are two problems with the classical theory. One is that it keeps going up. It's not coming down like this one. And also in the classical theory, any object will radiate waves at all frequencies. That means that an object with 1000 K will radiate X-rays, which doesn't happen, right? It doesn't radiate gamma rays. So scientists were trying to understand and trying to build a model, a theoretical model, to explain this blackbody radiation. So there are two prominent scientists who worked on this. One is Wayne, and the other one is the one who actually explained the blackbody radiation curve is Max Planck. Wayne looked at this black body radiation curves, and he found a relationship with the maximum intensity and the wavelength where we have the maximum intensity and the temperature of the hot body. So he found out that if you have a hot object with temperature T at the surface temperature T, that means he found out that the maximum wavelength for the high intensity, which is, say, if it is lambda max, he found out that T times lambda max is a constant. That means a surface temperature of the star is equal to that constant, which he called B, and then lambda max. So if you look at a spectrum from a star and you have this blackbody radiation curve here, and you find out the wavelength at which you get the maximum intensity. So this is intensity, this is wavelength. So the one here, right here, so we got temperature T1 and we got lambda 1. So if you want to find the temperature of the star, all that you need to do is you divide that constant by lambda max. So the constant divided by lambda max, which is the wavelength at which we got the high maximum intensity, is the temperature. So Wayne was able to explain the point where we get the maximum intensity. But he couldn't explain the curve, why it's going up and coming down like that, because their theory, the old classical wave theory, says that it keeps on going up. It reaches infinity when we get high frequency, but here it's going and coming down. Max Planck was able to build on the old classical wave theories and added the quantum aspects of waves to explain why we have the curves like this. So the old classical wave theory says that when particles oscillates, they emit waves. When particles oscillates, they emit waves, electromagnetic waves. He said that in hot objects, obviously that atoms vibrate, and when they vibrate, there's an oscillation. And due to that oscillations, they emit waves. So what's happening is that they oscillate between different energy levels. So this describes that an atom oscillating between different energy levels here, and the frequency is F1, F2, F3, F4, F5. And you can see that separation distance between these energy levels is low compared to this one, and we are going higher and higher. So these are higher frequencies. So the F5 is higher than all other frequencies where the oscillation is happening between two different energy levels at a very high distance. So the change is a bit higher than the other ones. So Max Planck said that the energy emitted or radiated or absorbed is equal to E is equal to HF. He said that you need to multiply the frequency by a constant to get the energy. So the energy is emitted as discrete quantities and not continuous. But the question is that why is that we are getting more energy emitted at a range here? Because we get less here and less here, looking at the curve. So his explanation was that an atom and oscillating between energy levels with a shorter distance, short difference, they're highly probable. So if they're highly probable, why is that at this stage that we don't have that much intensity compared to this one? Because although the separation distance between the energy levels here is low compared to the other ones, but the amount of energy or the intensity emitted is low. Like this is about throwing 2 kilogram balls, and this is about throwing 4 kilograms or 8 kilogram balls. So when you throw lots of balls, small balls, the total intensity is not that much compared to these ones. And so every object with a temperature has an optimum value where it will emit lots of radiation at a particular wavelength. And in that particular wavelength, there are more atoms oscillating. There are more atoms changing their state from this point to this point. That means that we have a high intensity. So as it go higher and higher, we see that separation distance between the two states is really large. And what's happening is that the temperature of the black body is not sufficient enough to maintain these oscillations or make the oscillation possible. And that's the reason at this range we're not seeing any intensity. So we're basically talking about two things: the quantum nature of the energy emitted due to these oscillations and between two energy states. That means that energy emitted is equal to constant time a frequency. Depending on the different frequency, that atoms actually change states between two places and they oscillate between them. And the second one is the probability. So the probability of having an atom oscillating between two states with the separation distance bigger is very less, and in some cases is impossible. And that's the reason that we don't get any intensity here at this space. So this formula is a breakthrough in terms of the quantum mechanics that Max Planck basically he built the foundation for the theory of quantum mechanics, and he explained the quantum nature of light and quantum nature of electromagnetic waves. And from there, Einstein developed another idea of this photoelectric effect, which is he came up with the equation that kinetic energy emitted by photons, the emitted electrons will have a kinetic energy which is equal to HF minus the work function. So sometimes people get confused between these two formulas. They're not the same really, because Max Planck explained about the quantum nature of the radiation emitted and absorbed by hot objects. But Albert Einstein used that concept to demonstrate that light consists of particles or photons, and when that photons interact with metals, they emit electrons, and those electrons will have a kinetic energy which is equal to hf, which is the energy by the Planck constant time frequency, minus the work function. So the work function is actually work function is equal to hf0, which is the threshold frequency. So this is kind of related, but Einstein basically got his Nobel Prize for demonstrating the quantum nature of light. And you might come across the other one, which is Niels Bohr came up with this atomic model where he explained that we have a nucleus and the atoms, the electrons go around in orbits and they have these stable states. So he used this idea of these changing states, changing energy states, which Max Planck used to explain the quantum nature of the radiation. So he used that idea. So they all developed from each other. So what Max Planck did is a foundation for quantum mechanics or quantum physics.